as in every live, is check the sound. So let's just check that out. So yeah. Oh, now I can hear myself live. Perfect. All right, so let's get rid of these. Hopefully you're hearing me on the microphone. So welcome to this live. So if you haven't seen me before, my name is Dr. Clara Ellis, and I am a particle physicist working at CERN. And I also make videos on various social media platforms to talk about particle physics, the research that we're doing at CERN, and many other things as well. So we're going to be live for about an hour, so please do get your questions ready. And this is essentially just a hangout. I'm going to go through as many different questions as I can in the time that we have, and let you lead the conversation through that. So welcome to the people joining in the chat. I can see that there are people here already, which is fantastic. I've got a cup of tea, which will probably be cold by the time we get to the end of this chat, because I never seem to manage to finish drinking the whole thing. But yeah, I'm looking forward to hanging out with you. So I'm live on 2 platforms, and I'm going to try and talk to both, but mostly the aim is for YouTube. And we've also got Bob from Fundamentally Explained, who is in the chat and is going to be collecting your questions and helping me out, which is really fantastic. So thanks again, Bob, for joining in the live. So we already had a bunch of questions over on Instagram that I put out a Q&A on stories before the live started so that we could gather some questions already. So I'm going to start with some of the ones that are already quite linked together. So I think it's a nice grouping of questions that we can go through all together. So you might have heard recently in the news or seen it written on various news outlets that there is talk of a potentially bigger collider in particle physics. Now, I want to start by saying that nothing is fixed yet. This is something that as a community we are discussing as a particle physics community, what we want to have potentially as a future experimental facility. And of course, we're also talking more broadly with the people that live in the areas where the various machines could be built, with various politicians, and just generally with everybody, since particle physics is now a global endeavor. It takes thousands of physicists, engineers, technicians, computer scientists, and people from all over the world to get the results that we're getting. And so it's really important that we work together as a community. Science isn't really like how it used to be, where you could have one person sitting alone in a study, sort of writing a few things down. You really do need to collaborate globally in order to get things done. So the questions that we had over from Instagram, and I had a couple people asking this question, so I'm sorry I didn't grab the usernames, but if you did post this question, thanks so much for sending it. So the first question that I wanted to start with, which is why aren't electrons used in colliders anymore? And this is a really important question. Why are we using protons in the Large Hadron Collider when in the same experimental tunnel we used to have electrons? And this is because electrons are much lighter than protons are. And so as they go around the ring, they give off what we call synchrotron radiation. And so this causes them to lose energy as they are changing direction. And so it happens more for lighter particles than it does for heavier particles. So with electrons, we were losing more energy, and eventually the more and more we kept accelerating them around the ring, the less useful it was becoming. So the next step going from this previous accelerator, the SPS, to the Large Hadron Collider that we currently have was to switch from using electrons and positrons, which are the antimatter particles of electrons, and go to protons, because these protons are heavier. So this was to enable us to go to higher energies, which was fantastic. And it enables us to have what we call a sort of search machine. That's what the LHC is. But the problem is that protons are not fundamental. They're not elementary particles. And so we can't, we can, hold on. need to drink my tea. So protons are not elementary particles, so we can break them up into smaller pieces. So they're made of quarks and gluons. And this means that we don't know exactly what collision energy we are colliding at, because even though we can get them to higher energies, when they collide, it's the constituents, the parts inside that are doing the actual colliding. So we would prefer to use electrons or elementary particles, but we need heavier particles. So then that's going to link. So that also answers another one of the questions that I got asked, which was, are quarks fundamental? Oh, no, it doesn't answer. Sorry. Okay, let's start again. So then the next question is, are quarks fundamental? And as far as we know, they are. So as far as we know, we cannot break quarks up into any smaller pieces. There are studies, there is research to see if we can break them up into smaller pieces, and there are theoretical proposals that suggest that quarks actually have a fundamental structure. But so far, we haven't seen any evidence of this in our colliders. So if we were able to show that there was internal structure inside of the quarks, that would be an incredible scientific advancement and advancement of our knowledge. But so far, we can't break them up any smaller. But what I wanted to say earlier when I was, is that if we could isolate quarks and use those to collide, that would be really interesting too, but we can't do that. They don't live on their own. They have to buddy up with other quarks as soon as possible. Okay, so then to go back to the electrons and the protons, the question is, do we need a bigger collider? And actually, the answer is not necessarily, but this is the discussion that we're having right now in the science community. So the question is, we want to go to higher energies, or we want to be able to probe new regions of physics that we haven't been able to study yet. And so to do that, we need either a bigger collider so that we can keep colliding with the similar particles and technology that we've already been using and go to higher energies, because we lose less of the synchrotron radiation, because with a bigger collider, that change in direction is less. And so that's one of the options. And so, for example, at CERN, there is this proposal for the Future Circular Collider, which would be a 91-kilometer long particle accelerator compared to the Large Hadron Collider, which is 27 kilometers long. And so then you could start, for example, with an elementary particle like electrons and positrons, and be able to very precisely study things that we already know about, and precision measurements allow us to compare the theoretical proposals to the data that we have. And then potentially you could swap out this electron-positron machine for a hadron machine like we did with the SBS and the LHC, and then be able to use the same experimental tunnel with hadrons and go up to higher and higher energies and go again for what we call a search machine. But there are other proposals, other types of colliders that are being discussed. So we're also discussing linear colliders. And so rather than having a huge circle, you would accelerate the particles in a straight line, essentially. And this way you don't have any synchrotron radiation because they're not changing direction. And that's one of the proposals. And then there's also a discussion, for example, of having muon colliders. So muons are the heavier cousins of electrons, but they're still elementary. They still can't, as far as we know, be broken up into any smaller pieces. And so this then would enable us to go to higher energies. There'd be less synchrotron radiation from the same circular size. But so far, we haven't built facilities with muon colliders before. So this is a newer type of technology with lots of sort of engineering challenges and building challenges. But also that's something that we're excited about in physics anyway. We love a good challenge. So the community is discussing all of these different options and trying to plan really for the next 70 years of particle physics. So what do we want to build in the medium term? What do we want to build in the long term? What does each option, what avenue does it then give us in the future, and what avenues are then less likely to happen? And it's not just, for example, at CERN, it's really globally. There are many countries that are discussing this, so potentially colliders in other places around the world too. And then I see, in the comment, there's also a question that there's plasma wave field acceleration. So this isn't the proposed technology for the linear colliders, but it is being researched very actively. It's a very interesting field of research. This is using plasmas to accelerate the electrons. And so really it'd be like the electrons are surfing on a wave of plasma. And this is something that potentially could be used as an upgrade to a linear collider. So that's a really interesting area of study as well. Okay, brilliant. So let me drink some of my tea without spilling it everywhere, because I have a very bad habit of making my tea very full. And that's because I want as much tea as possible in my mug. So I see a question up here that says, do you currently work at CERN? So yeah, if you haven't met me before, my name is Clara, and I work for the University of Amsterdam in the Netherlands, and also with NICAF, which is an institute in the Netherlands. But I am working on the Atlas experiment at CERN. So I'm what's known as a user. So this is somebody who has an association with CERN specifically for the experiment that I'm working on. And so I travel there frequently. I spend a lot of my time at CERN working on the experiment and collaborating with different colleagues at CERN. But I'm not 100% at CERN in terms of where I live. I also live in the Netherlands. So I see a question down here, so I'm jumping around. What's your favorite CERN club for the downtime? That's a great question. So CERN, maybe I can go back a little bit. CERN is a community of many people, tens of thousands of people work at CERN and are visiting and are coming back and forth. And so some people live out at CERN, and some people are just visiting for a short while. And so there are a number of clubs for people to do recreational activities while they're out there. There's a board game society, there's a skiing club, music, a bunch of other ones. My favorite one that I did, it's not going anymore, but a friend of mine ran a wine teaching course at CERN, and before I did Kat's course, I just knew I kind of liked dry white wines. I didn't really know anything else about that. And I also honestly didn't think the course was going to be for me. I thought that I wasn't the kind of person that knew about wines. And then I turned up to the first session and she'd accidentally bought too much wine for the number of people there. And we just had such a fantastic time talking about these wines and learning there's a lot of science behind it about why the different grapes taste the way that they do, and I just really enjoyed it, and it was such a nice communal activity. So that's what I liked doing. Also a big fan of skiing. I'd never skied before I moved to CERN. It wasn't something that I'd done when I was living in the UK, and then when you're only an hour from the mountains and you can just hop in someone's car and go skiing for like 25 euros. It's a bit more now, but it was a really great opportunity to go skiing, and then swimming in the lake as well in the summer is really nice. So brilliant. So let's do some more questions. So the other one I wanted to link together is, why don't we smash neutrons? So neutrons are similar to protons, but there's one key fundamental difference, and that's that neutrons are neutral and protons are positive. And we need the magnetic field to be able to bend the path of charged particles. And so neutrons, they don't bend in the magnetic field. And so we put them in the LHC and they go straight forward and fire into the side of the tunnel, and that wouldn't be very good. So we don't use neutrons, we use protons. So I see in the chat there's a question that somebody said they keep hearing rumors about the FCC. Any news? So this is a long process that's going to take a while, because we really want to make the right decision and consult many different communities in the decision for the Future Collider. So you're hearing about it now, and that's because it's a big discussion topic and it's going to keep going. So next year there's going to be a report from CERN. So 2025 is one of the reports that's going to come out, and that's when we will have more of an idea of what's going on. So it's going to be a long process. Okay, brilliant. So let's have a look. So I see one of the questions here from YouTube is, what kind of tea are you making? Do you drink a lot of tea when you're working? So I'm British. I mostly drink English breakfast tea with milk because I'm a stereotype. And my favorite tea is Yorkshire tea, also because I have family from Yorkshire, and so it makes me feel like at home to be able to drink that tea. This isn't sponsored. They don't sponsor me. I just really like the tea. But yeah, really, I just love English breakfast tea. I do drink other types of tea too, especially when I've run out of milk, and my colleagues like to make fun of me because I am a stereotype. But yeah, I mostly drink English breakfast tea with milk. Okay, so I also saw that there were questions about what it's like to work at CERN, and I did get a fantastic comment on one of my videos, and I think Imogen's in the chat right now, about a day in the life, and I would love to do a day in the life. The problem I have at the moment, and the reason that I haven't done it, is because my days all look very different, and so it's a bit disingenuous to show you just one day, because I sometimes, like when I was a PhD student, I was spending 95% of my time either in the lab testing new sensors, because I did my PhD on prototypes of new devices that went into the Atlas experiment that I worked on, or at what we call test beams, which is then when we took those prototypes, put them inside of a beam that we took from, I said the SPS earlier, and I'm getting confused because it's very late. I shouldn't do these lives at late. So when I said the SPS earlier, what I actually meant was LEP, the Large Electron Positron Machine. So that is the electron positron accelerator that I was referring to earlier, when we used to have the electrons and positrons in, and then the LHC. So the SPS is the accelerator that we currently have that feeds into the LHC. And so I used to do my PhD with particles that we diverted off from the SPS, collided into a target, and then that gave us muons to, sorry, I see a funny comment in the chat that says, not to get too controversial, but R1, R2, or Prevosan, so I'll come back to that one. So we used to divert, or we do still divert, these particles away from the SPS, collide it into a target, and then we have muons that we can use to test prototype detectors for our sensors. And so as a PhD student, this was 95% of my time was either in the clean room or at these test beam facilities. And then I also spent time reconstructing the data and doing programming. And then, also a lot of time in meetings and discussing with colleagues. Whereas now I've sort of transferred a little bit and I do more data analysis. So I study the top quark, which is the heaviest particle that we've discovered so far. It's a quark. And it's in the 3rd generation. So it's a really interesting particle because it allows us to do what we call precision studies. So we want to, I've mentioned precision a couple times already, but what we want to do is very precisely measure the properties of all of the particles that we know about already from the standard model, compare them to predictions, and start to see where these predictions and measurements differ, because we know that this standard model of particle physics that we have doesn't explain everything. It doesn't explain gravity. It doesn't tell us what dark matter is made of. It doesn't explain why there was slightly more matter than antimatter in the beginning, in the early universe, and a couple of other things like where neutrinos get their mass from. And so we know that at some point it's got to break down. It's got to stop being so accurate. And almost the problem at the moment is that it's too perfect, and we keep trying to test where it breaks down, and it's doing too good of a job. So by doing precision measurements, we're trying to look for these small differences. And then also with the top quark, we can use it to test how it interacts with the Higgs boson. And potentially, if, for example, dark matter changes into something that eventually leads to top quarks, which could happen because we know that dark matter is massive, and so perhaps the most massive particle is involved in the final stages of it, then we could potentially find out what dark matter is or find out new particles. And so it's a really interesting particle to look at the studies, both precision and searches for new types of particles. And so in this case, a lot of my day job is programming, is in meetings, discussing with other colleagues what we want to do for next stages of the analysis. We have big collaboration meetings where we talk with lots of us all together. And so if I just showed you that day, it wouldn't reflect the time I spent in the lab. I also spend a lot of my time in the control room, taking data in the control room. So we have different responsibilities of people at different desks in the control room. You can think about it a little bit if you watch Star Trek, like being on the bridge, where each person has a different role. You have somebody who's the pilot, you have somebody who's the captain, you have somebody who's doing comms. And so we have different desks in the control room, people responsible for different things, and we're all communicating with each other and also communicating with the Large Hadron Collider control room. So that's called the CCC. We have a safety officer that's making sure, for example, that absolutely nobody has managed to go down in the tunnel, which would just automatically trip the beam and turn it off anyway. But just to be safe, they're monitoring that, and they're monitoring a lot of the alarms that we have in case there's any sort of smoke detected for any reason. So that's also a big part of my job, and I do a lot of programming, things like that. So I would really love to make this video. I saw the comments, so thank you so much for asking. But I want to make sure that it's an accurate reflection of what it's like to be a particle physicist, because there are lots of different jobs that you can do as a particle physicist. You can do machine learning studies, you can do statistical precision measurements, you can be one of the people who's helping to define which data that, or not just helping, but defining which data we want to keep, because we cannot keep all of the data from the collisions. So there's many different roles that people can do in as a particle physicist. Okay. So also I see that there's a question about the CERN Summer School, and a couple of people asked me this on Instagram before the live as well. So I want to address that the CERN Summer School is a fantastic program. It usually opens up for people to apply to sort of at the end of the year, going into the early next year, and then around about like a few weeks ago, I think it was, that people were finding out whether or not they were, oh, hold on a second. All right, we're just gonna, my phone changed its color to red because it's getting late, but I don't think that changes anything that you see. So it is a really fantastic program. I never did it. I did not apply to the CERN Summer Student Program because when I was at university, I worked every summer to make money, to keep myself going throughout the rest of the year. I did, to be transparent, I did have some support from my parents, and I got a loan from the government. So this money was to give myself some extra buffer, be able to pay for nights out and things like that, and just have that little bit of extra cash. So I only worked in the summers. I didn't have to work throughout the year, which was a privilege. But I didn't know that the CERN Summer Student Program had a sort of per diem that they give you. So they support your accommodation and food and travel to CERN, and then they give you some money while you're there. And so I didn't apply because I didn't give myself the benefit of the doubt, and I thought I wouldn't get in, so why should I apply? I knew that they took, they were looking for people who were really enthusiastic and stuff like that. And of course I was enthusiastic, but anyway, I just didn't think I'd get in, and I didn't think I could afford to go to Switzerland for 3 months. That was a mistake, because you do actually get funded to go to CERN during the CERN Summer Student Program. And my advice is always let them rule you out. Don't rule yourself out. It's so much better to apply And of course, it's not going to be possible to get into every single one of these programs, but if you apply to 5 of them, you've got 5 chances to go and do something interesting and exciting during the summer. So if I could go back in time, I would have told my past self to apply. But you also, if you don't get in, and it's really hard to get in, there are so many people, so many fantastic people I know who applied, who didn't get in and are still working at CERN. The thing about if you want to come and work at CERN is just to keep applying for different programs and to keep building your skills in many different ways. So if you're at an undergrad university and you're lucky enough to have a department that works on CERN research, then you can always ask them for an internship. So it wouldn't be going to Switzerland, but you can work with your professors at the university and get some experience doing some data analysis. Maybe you can help out in a lab. Maybe you can do that over the summer. And it's a really great opportunity that then if you want to apply for a PhD, that's a great thing to be able to put on your CV. So not getting into the CERN summer student program does not stop you from getting into CERN later, but I do really encourage people to apply if they can. There's a bunch of other summer schools as well, which are also fantastic. So there's also the DAISY summer student program, which is in Germany. That's a great program. I've got friends that went to that one. There are other summer schools. So for example, there's the HASCO summer school that's going to take place this summer. So they already closed applications for this year, but you can always apply for another year. And it's really just about trying many different applications and giving yourself the best chance. So not getting in does not mean that you're not going to be a fantastic scientist or you're not already a fantastic scientist. It just meant that the dice didn't roll that way this time, because really they do have way more people applying than they can take, and so it's no reflection on you that you didn't get in if that applies to you. And also take a look at your eligibility, because I'm pretty sure most people have 2 chances to apply. So if you still have another chance to apply next year, then that's a good option, is to try again. And maybe later on this year I'll try and do either a video or perhaps a live or something talking about the kinds of things that you can do to, show your enthusiasm in your application. If that's something that people want, then I can add that in. So I saw a nice comment up here that said that they loved the behind the scenes peeks. So I really appreciate that people like to see the behind the scenes, because that's something that I really like to do in my videos. So one thing I want to say while we're here is, if you are enjoying this video, if you enjoy the behind the scenes, thanks for the link, the behind the scenes that I show in my videos, then please like this video. It helps to tell the various platforms that more people would like to see this. And also, if you're not subscribed already, I would really appreciate it if you do. On YouTube, I'm really trying to reach 10K. I know it's just a number. I know it doesn't change anything, but it's just a nice milestone and it would make me happy. And so if you want to see more science content and you want to support these kind of videos, it's free, and I would love if you could sub. Also, thanks for the comment about the haircut. I got it done yesterday because it was getting too long and annoying. So thanks. Okay, let's have a look at some more questions. So there's another one that kind of links to what I was talking about before, which is, at what point in your life did you decide to study physics or particle physics? So this is a great question, because I have always loved the surrounding of science. I love working out and understanding how things work and how our universe works and how plants grow and all those questions that you ask as a kid. And I was fortunate to have people around me who were also really interested in these topics and either answered my questions or encouraged me to go and look for places where I could find out the answers. But I actually, for my high school, I had fantastic teachers, but we didn't have a dedicated physics teacher when I was there. So I very nearly didn't do physics. I was looking at my options and I wasn't sure what to do. And it's only because my mum is a primary school teacher that she knew that I could take it as another option at a different school whilst still staying at my school. I had all my friends there. I didn't want to leave. And so I was able to go and do physics for my A-levels at a different secondary school, which I think was also a fantastic experience, because whilst I didn't want to leave my high school, I went to this new place. Twice a week I was I was an outsider, so I had to make friends again. And I did physics almost in a kind of university style. I turned up, I did the lectures or did the lessons, and then I had to go away and sort of do my homework by myself at home. So I think that was really good practice as well for university. So I think the experience was good for me. And then when I was picking the courses that I wanted to do at university, I was choosing between English, which is a course I really enjoyed at school, and physics. And in the end, for me, and this was just a personal choice, I thought that the things I was learning in English, I could learn outside of university. You know, it wouldn't have been as immediate as having access to fantastic lecturers, but I could read around the topic at home. Whereas if I wanted to learn physics, I really thought I had to be in a lab, I had to do the experiments, I had to go to the lectures and really get very hands-on experience. And so at that point, I thought I was going to do astrophysics because I really loved astrophysics side. And then I got to university, I kept my options open, I tried a whole bunch of different courses, and as the sort of years went on, when it came to choosing my master's topic, one of the professors said, hey, do you want to come and do this research project in my group? It's studying the top quark, which is now what I do full time, and it's with the experiment at Fermilab, and there's a potential chance we'll send you to Chicago at the end of it, but no promises. And that was enough for me. I was like, this sounds amazing. It's real research, which at the time, not every single project that you could do was on real research. So it was doing real measurements with an international team. And then at the end, they did end up sending me to Fermilab to be a summer, like kind of a summer student. So it wasn't the CERN summer student program, but I got to do this analysis again for another 2 months at the end, write it up, give a presentation to scientists. And by that point I was hooked and I really wanted to do a PhD. And a PhD is a fantastic time to really see if you enjoy this research more, because that's when you're an independent scientist. You still have supervisors who are going to guide you, but that's the point where you're starting to do the research that you want to do. So it's kind of been a long process. I didn't know for sure when I started my undergraduate at university, for example, that I was going to stay in physics. And that was one of the other motivations, actually, that physics allowed me to keep many options open. So I could still go and be a teacher. I could work in industry. I could stay in research. I could go into finance. That I kind of knew already wasn't something I wanted to do. But there were so many options with physics that you could do afterwards that I thought it was a degree that kept my options open. Brilliant. So as usual, I am way too behind on all the questions. So, okay, let's link this in because I think it's really relevant, and then let's go to some of the more physicsy questions again. So how to become a particle physicist. So if you want to be a research particle physicist, then my advice is that you should so at high school, do as many science, physics topics as you can and try to apply to a university to do physics. This is, if you want to be a researcher, you do need to get an undergraduate degree, and then either mine was an integrated master's, or you do a bachelor's and then a master's afterwards, or I guess in the US you do a bachelor's and then an integrated master's PhD. Either way, there's 3 degrees: bachelor's, master's, and PhD, and you're going to want to try and do all of those. If you can pick a university that has a particle physics department, that's really going to help you out. It's really going to allow you to do internships with the group. You're going to learn from people actively doing that research, which is going to be a really great experience. But if you can't do that, don't worry about it. It's okay. Just do the best you can in your courses. Try and read around your subject. You can watch some YouTube videos, ask a scientist who's working at CERN to give you some pointers on where you can go and do summer student programs, for example, and just keep applying to every opportunity. And then if you want to work at CERN, you don't have to work at CERN directly. So that is one option, but you can also work at a university and be sent to CERN, which is what the majority of people do. And so that's a fantastic opportunity if you want to become a particle physicist. Somebody asked if I was related to Taylor Swift. Thank you so much for the compliment. I view it as a great compliment. I'm not related to her, but it's very kind of you to say. That's a question. Sorry, I don't mean to laugh at these, but some of them I find very interesting. What is the link between Orthodox Easter and CERN? None. So for some reason, whenever we restart the Large Hadron Collider, so it gets shut down every winter, and this is to conserve energy, because we use energy for our research. And in the Northern Hemisphere winter, we need a lot of energy for heating homes. And so we have to be off once a year anyway for maintenance and upgrades. And so we choose to be off in the winter in order to coincide with the time when most energy is being used in the surrounding area. And then we turn back on again in the spring. And for some reason, it always ends up being Easter when we turn on again. And there's no reason. I probably shouldn't say this. This is going to spark more stories, but there's absolutely no reason about it. I reckon the whole reason is that the people in the control room and the people running the accelerator think if we haven't turned on by Easter, we're late. And so even though Easter moves around, that's kind of like the latest that you want to start the accelerator. But there's no reason for it, except for it's after the winter. And somebody said that they like my t-shirt. Thank you very much. This is an event display from the Atlas experiment, and it was a t-shirt we got when we restarted for run 3. So it was to sort of commemorate the start of the 3rd run of the Large Hadron Collider. Okay, let's have a look. So Eric is asking, are there any advances finding the graviton? So this is a great question. So the graviton is a hypothetical particle that is linked to gravity. So out of all of the force particles that we have, gravity is the final force that we don't have an associated particle for. And some people believe that it shouldn't have one, that it's not the same as the other forces like electromagnetism, that it doesn't have a particle that is responsible for the force. And other people think that there should be a particle. And so it is something that we look for. But so far we haven't seen any evidence of it in our data. And to discover it would be an incredible leap in scientific understanding, but it's not clear if there really is one. So it's something we search for, but there's been no evidence for it so far. So there's another question also. Did you find any kind of antimatter in the experiments? And yes, we see antimatter all the time. So it is created frequently in our experiments because matter and antimatter are created pretty much equally, but not exactly. And that's the problem, that in the early universe, we think that there were equal amounts of matter and antimatter, and then through the process of particles changing into one another, slightly more matter was left over. And then when they collide together and annihilate, because like an electron and a positron come together and they annihilate, then we were left with just photons and energy. And so then we were left with just mostly matter left over. But antimatter is something that is created frequently in our collisions, and we even have a dedicated facility on site that we call the Antimatter Factory, which I think is actually a good name, whereas a lot of our naming is pretty terrible. And so at the Antimatter Factory, we are filtering off the antiprotons and the positrons, and sometimes creating antihydrogen in order to study antimatter more closely. So I'm also working on a long form video. Long form is something that I haven't managed to get out many videos for, but I'm working on it, all about the most recent result on antimatter. So that should hopefully be coming out very soon. And I will talk a lot more about that in the video. And I also have a colleague who kindly showed me around the facility, and we took a behind the scenes look at the experiments in the antimatter factory. So let's have a look at some more questions. So thanks again to Bob, who's doing a fantastic job getting all of your questions from multiple platforms and collecting them all together. So thank you so much. So let's have a look. So there's a question, so it says, can you talk a little bit about the God particle? So the God particle is a name that we give the Higgs boson. I say, we don't give the name to the Higgs boson. The Higgs boson is sometimes called the God particle in the public understanding, because I think it's an easier name to remember than the Higgs boson directly. But it was a name given by one physicist who was going to write a book, and he wanted to call it the goddamn particle because it had taken a very long time to find it. And his publisher was like, you can't call it that. you won't be allowed to call your book that. And so he called it the God particle because it's sort of the particle that gives mass, and it was a very important particle, and that's the name of the book that got published, and then that's the name that kind of got out into the public understanding. But it's the Higgs boson, and the Higgs boson is the particle that is associated with the Higgs field, and the Higgs field is all throughout our universe, and by interacting with this field, elementary particles get mass. So an electron interacts with the Higgs field and it gets a little bit of mass, and a top quark interacts with the Higgs field and it gets a lot of mass. So the amount that it interacts with the field is how much mass it gets. And for example, it's not clear that where neutrinos get their mass from, so we don't think they get it via the Higgs field, but then that means we have to understand where they get their mass from. And we want to see if every particle interacts with the Higgs field as much as we expect it to. And perhaps because dark matter has mass, it might also interact with the Higgs field. It might get its mass from that, or it might get it through a completely different process. And so by studying the Higgs field, we're also now able to look for different avenues for dark matter. And this is also why sometimes you'll hear the word portal related to particle physics, because a lot of my colleagues like to talk about this link between dark matter and the Higgs field in a scientific sense as a portal from one to the other, just meaning that they have a connection. But of course, the public understanding of portal is like stargates and travel and intergalactic stuff. And so there's a miscommunication there between what that word is actually being used for. So if you hear the word portal, it just means a connection, like a link between one area of research and another. It's unfortunately nothing to do with being able to travel anywhere quickly. So someone's asking if there's another term for portal. So it's just a link. It's just a connection. Okay. Let's have a look for some other questions. Oh, there's one question. How hot does the particle accelerator get? Well, it's actually very cold. So the magnets that we use are superconducting, the dipole magnets that are used to direct the protons around the ring, and they go down to 1.9 Kelvin, which is 1.9 degrees above absolute zero, the coldest possible temperature in the universe. And so what we have to be really careful about is not having the accelerator heat up at all. And so we have many features that are to reduce the chances of heat reaching those magnets. Because what would happen if the magnets warm up too much, then they stop being superconductive, and superconductive means that there is no electrical resistance going through the wires. And so we have 12,000 amps going through these magnets, and so if they suddenly stop being superconductive, there's suddenly a whole bunch of resistance, and that's not so good for the magnets. So this is what happened in 2008. There was a short circuit, one of the magnets, and just a small tiny amount of heat, really, like, we wouldn't even notice it, but it was a small amount of heat which caused that part of the magnet to go above its superconducting state. It was no longer superconducting, and it just kind of like the magnet like moved, and it moved, I think, I can't remember, but it's like this much or something. It moved out of place, and it was, it was quite a bit of force to move a magnet that's very heavy. But then we had to warm up the whole sector, remove that magnet, put a new one in, train it again. So you have to train these magnets. You have to keep getting them to do mini quenches so that they can get more and more and more electrical current through them. And then we could start running again. So we were supposed to start in 2008, and we actually started collisions in 2009 because of this very small sort of missed, like, bad connection in the magnets. And so every single one of them also got tested in order to be able to guarantee that it wouldn't happen again. So it's not that, so when you're asking how hot does it get, it's very cold. Parts of it are around 1.9 Kelvin, and we try and keep it at 1.9 Kelvin. So Ray asks, do you own your own particle accelerator? This is a great question. I used to. It really depends on what your definition of a particle accelerator is. So when I say I used to, those cathode ray tube telescopes, these like really boxy televisions, boxy televisions that we used to have before everything got to be flat screens, those had particle accelerators inside of them. So there was an acceleration of electrons that were fired at a screen, and then you saw the image on the screen of the television. And so we used to, but not anymore. These televisions aren't there anymore. But you could say that a microwave is a particle accelerator. You could say anything that creates light, maybe. But when we're talking about a classic particle accelerator, especially a circular one, then no, I don't own my own one. I know that there are some universities build little ones to be able to study them, and really the next size up that you get is in hospitals. So particle accelerators can be used for medical treatment, medical hadron therapy for cancer treatment. And these are sort of room-sized particle accelerators that are accelerating protons. And what happens is that when the protons, because they're heavier than other particles, they have what we call a Bragg peak, which means that their energy kind of is a certain amount, and then it all gets deposited right at the very end of their path. And so if you can tune these accelerators very precisely, then for example, if somebody has a tumor in their eye and you really don't want to irradiate the brain, this is where we live, or if for example somebody has a tumor in their spine and you want to keep it away from other really important parts of the body, then you can use hadron therapy to very precisely deposit the dose in the tumor and try and keep that tissue healthy, especially if you either rotate, you usually rotate the accelerator around the patient. And so then that's the next size up of accelerators. And then there are thousands of accelerators around the world, all doing different jobs, especially some types of accelerators are specifically used for that synchrotron radiation. So if you were here at the beginning of the video, I was talking about how annoying synchrotron radiation can be for particle accelerators that we have at CERN, because we want to go to as high energy as possible. Well, you can use synchrotron radiation in order to do studies with that very direct beam of photons. So sometimes we use it for intentional reasons rather than just having it be something annoying that is reducing the energy of our particles. There's a question asking, am I planning on staying at CERN? So yes, I'm very fortunate that now I have a permanent job. So my job at the University of Amsterdam and with NICF is permanent. So I'm planning to stay for the foreseeable future, as in like the rest of my career, I hope. And I really feel lucky that I can work with fantastic colleagues and also keep doing my research at Amsterdam. So my plan is to stay working at CERN. There's a question, do physicists make a lot of money? This is a good question, and it's really relative. So for me, I came from a stable background. I'm very grateful to the sort of background I have with my family, but it wasn't particularly affluent compared to like a lot of friends I now have who maybe went to private school or stuff like that. So for me, I'm making a lot of money. I'm very happy with the wages, and I'm not going to say the direct number, but you can very easily look it up. I work for a Dutch university. I'm an assistant professor. It's very easy to look up my pay scale online, and you can look up also the pay scale of different people, of postdocs in the US, for example, or fellows at CERN. You can look up the different pay scales. And also, slightly frustratingly, you do get paid differently depending on the country that you're working in and yeah, different roles get paid slightly differently. So you can have people at CERN doing the same job who are getting paid slightly differently, but everybody who's sent to CERN to work should also be getting paid extra because Switzerland is so expensive. But for example, I know people that are earning double my salary, if not more, because they went on to be consultants or work in finance or work in various industry positions. So compared to potential salaries I could get with my skills, with my training, then it's the possibility to earn more money elsewhere. But personally, for me, I'm not in it for the money. And again, that's a very luxury position to be in. I'm comfortable now. I love my job. I'm so fortunate to get to work on research and do something that drives me intellectually and keeps my brain busy. And I get to work with amazing people from all over the world. In fact, one of my favorite things about my job is that I get to sit in the restaurant at CERN and hear about 15 different languages being spoken around me of people from all over the world, from different places. And I just think that that's a really fantastic environment to be in, a really healthy environment to learn from each other. And so I really like it. Also, thanks so much to the person in Facebook who said, please pay Clara more. So not Facebook, sorry, TikTok. I appreciate it. But anyway, I'm not advocating for that. But if you do want to support these videos, let's have a link like that. Please subscribe and like the videos, because that really is the best way that you can help me to make more videos. If you share it with your friends and family, that really helps me to make more. So I never want to charge you for videos. I want to make sure this is free, because I know that there are people who do not have the means to pay for this kind of content, and I just don't think that it should be behind a paywall. So if you want to support the videos that I'm making, the best thing that you can do is, give the video a like and subscribe to my channels. Thanks. So Imogen is asking, do you write scientific papers? So yes, I do write scientific papers. The interesting thing about CERN is that we have to, for example, in the experimental collaborations, so for example, Atlas, where I work, we have to do what we call a service task in order to be able to sign the papers coming from the collaboration. And once you've done that, you sign every paper that is then written using the data from Atlas. And so I've actually now got about 900 papers or something on Inspire. But honestly, I did not write all of those. It's just because I get to sign the papers. I've written, I actually don't know the number, 15 that I've directly contributed to, maybe 20. I wrote papers for the test beams that I did and the studies of the prototype pixel detectors when I worked on those, and then I've also written papers within my top quark research, and I've written papers when I've collaborated with colleagues on machine learning. But also, for example, you don't necessarily write the paper directly. Sometimes you're just reading and giving comments, and you've contributed in different ways. So particle physics is a really collaborative field where we share out the work, and then everybody gets to benefit from all of the fun stuff. So somebody asks, where can we find the papers? So you can easily search my name on Inspire HEP. So you can look up any physicist on there and you can read their papers. Also, I think if you just search clarinalist and Archive is the best place to go, because Archive is free. So speaking of stuff not being behind a paywall, Archive is a fantastic resource to read, especially physics papers, for free online, because we do what's called, so we do a preview paper. So we put it online as it's getting sent to a journal, and then even after it's been peer reviewed and published in the journals, we update the archive paper. So it's a fantastic free resource if you want to read anything to do with CERN. And also on top of that, CERN has a policy that all of our papers should be freely accessible, so you shouldn't ever hit a paywall for any of the papers if you want to read them. So I saw a nice comment saying there are amazing questions here, respect to you all. I haven't got to read everything in the chat. Bob's doing amazing work managing it. But from what I can see, the questions have been fantastic and everyone's been really lovely. So that's really, really great to see. Does Archive have a TikTok or a YouTube page? That's a great question. Oh, and Yost says, I don't think I've ever heard your last name. My last name is Nellist. So Nellist. So you should be able to find it there. But you can read, there's lots of great papers. Somebody says, hello, governor. Yes, I am British. Great. Oh, yes, Aaron, thank you so much for mentioning. Oh, yeah, and Bob says the archive you spell with an X. So he's put the link in the YouTube chat for how to access archive. And I recommend going and reading papers. That's a really great way to build up your knowledge about particle physics. Yes, Aaron says, can you talk about your upcoming public lecture at the Perimeter Institute? Do you have any other public lectures like that lined up in the future? So thank you so much for reminding me, because I did mean to do a shout out. So on Wednesday, I'm going to be at Perimeter, the Theoretical Institute in Canada, in Waterloo. And I'm going to be giving a live lecture to an audience. So sadly, I believe that all of the in-person tickets have gone, but they are also going to be I can't talk anymore. They are also going to be streaming it on their YouTube channel, and so you can watch it for free and from wherever you are if you visit the Perimeter YouTube channel. So I'll also make sure to post it in the community tab on YouTube and then all social media. So it'll go everywhere. So you'll find out about it. But yeah, thanks for mentioning, because I should really give a shout out now for people to go and watch that. So I'm very excited about being there this week. Maz is asking, do I have a degree in particle physics? Yeah, I have an undergraduate master's in physics and a PhD in particle physics. Those are my degrees. Thanks. Bob says he'll link the Perimeter Institute link at the end of the stream in the chat as well. Brilliant. Okay, so there's a question that was also, did you really capture a ghost? So this is one of those cases where a new study comes out and somebody uses an artistic word to sort of capture the imagination of the study, and then it is misleading, and then people misunderstand it because it's not a ghost. It's not in the sort of mystical sense of some person's essence that's still hanging around. The study was looking at the fact that there are sometimes spots of how do I best describe this? So I'm planning a video on this, but the reason it hasn't come out yet is because I'm still trying to work out the best way to describe it. But basically, with the magnets that we use on the Large Hadron Collider and on the other accelerators, we have dipoles which change the direction of the particles. And then we have higher order magnets that focus the beam in different ways. And sometimes you get higher order uncertainties, which causes a little bit of instability in the beam. And they didn't fully understand where these instabilities had come from. So what they do is that they simulate the magnets and the way that the protons go around the LHC and try to recreate these instabilities in the simulations. And it wasn't clear where they were coming from, and it had been a long-term sort of curiosity with the accelerators, and they finally were able to work out where these instabilities were coming from that were causing the beam of protons to sort of get knocked around a little bit more than they wanted them to. And so they called it a ghost, or it was called a ghost in the article, in the public article about it, because it had been something that had been around for a while, and sort of a mysterious thing causing the uncertainties. But it's not like, as I said, it's not a mystical essence of something. It's just a scientific thing that was left over, and therefore now they understood it, and so they said they've now discovered what that ghost was. But it's not an actual ghost. I hope I explained that well. I will explain it much better in the longer video when that comes out. Okay, let's have a look at some more questions. There was a question. Yeah, so Eric is asking, is it true that dark matter surrounds us, but we don't see it because it doesn't interact with photons? So exactly, this is where the term dark comes from, is because it doesn't interact like electromagnetically like regular matter does. And so therefore we don't because we just can't see it. It doesn't interact with photons. A better name for it is invisible, because dark is kind of the photons would be absorbed, and that would be something that's dark, but actually invisible, they just pass right through. So dark matter is passing through stuff, and it has a gravitational effect, but it doesn't have a visual effect. We can't see it. So it's invisible matter is a better name for it. Somebody says, who are you going to call? Ghostbusters. So Maz says, was it hard studying physics? Because I'm going to university to get a STEM degree. I think yes and no. So it's not easy, but it's not impossible. And really, with physics at least, it's just about doing problems over and over again. So you have to study the mathematics, and you have to go through the problems. So really, my best advice is, when you get homework, do it. And if you don't understand something, try it first, and then go and talk to your professors and discuss it with them. And that's really the fun part, is discussing all these like big ideas about how the universe works on the biggest scales, on the smallest scales, and materials and everything in between. How does stuff work? And you, as part of your degree, get to talk with really interesting people about all these different concepts. And so if you don't understand something, the absolute best thing you can do is to talk to the other students on your course, talk to your professors, talk to your tutor, go through the problems, and then you don't even realize that it's hard because you're having such a great time doing it. So it's definitely, I wouldn't say it's easy, because I don't want to minimize the fact that there are difficult parts about it. And if anyone's struggling, it's the worst thing you can hear is like, oh, but it's easy, when it's not. I definitely struggled too, but you just keep at it. And realize that if you're feeling stupid, that's because you're doing something like that is at the very edge of science, and people are learning for the first time. And so that's all part of being a scientist. Okay, brilliant. It's hit the hour mark, so I do also want to wrap up kind of soon. So there's so many fantastic questions that I will try and either make some shorts to answer these short videos to answer these questions, or reply to people where I can find the questions directly, or we're going to do another live sometime soon, maybe in the next maybe in about 3 weeks time, and we can discuss all of these questions again. So yeah, so Bob says in this chat, feeling stupid is part of the process, trust the process. So I definitely agree that yeah, it's just part of doing this kind of work. And I think that also applies to a lot of different careers as well. I think a lot of degrees that you'll do at university, or when you study something, you're never going to get it the first time, and that's fine. And it's about reading it from different perspectives, like some people learn better from books, some people learn better from videos, some people learn better by discussing things, some people learn better by doing problems, and you have to do all of these to sort of build up your knowledge from different sides. And so it takes a while, but it's the fun part, and that's why you should do it and enjoy it. Okay, let's see. So there's a question that I can answer quite quickly. Is it possible to observe Higgs decaying to two gluons in energy collision? No, I think. Hopefully I haven't embarrassed myself. Fortunately, it's the end of the video. Maybe my colleagues haven't made it this far. No, I don't think so, but I'll double check that. There are gluons involved, and you do have quarks coming off, but I don't think you have Higgs directly to two gluons. So, okay. There's a question. What can Atlas do with the lead-lead collisions during the ion physics period for Alice? So we also collide, as well as colliding protons in the Large Hadron Collider, we also collide heavy ions. Yeah, so there's a Quantanaut, I've never said your name out loud, says, no, I don't think you have two gluons. No, I didn't think so either. I just didn't want to embarrass myself on live. This is the fun and the challenge of going live, is that people ask really good questions, and then I'm not entirely sure. But I think it's also, okay, I'll come back to this other one, but I think it's really important to also show that physicists don't know everything. I'm not a walking encyclopedia. My job and my skill is to do the programming and to sort of apply the selections to our data. I do machine learning, we discuss with each other, but I don't remember everything up in my head. I have to look up a bunch of things and I have to double check things. And sometimes things that you thought were definitely true, it turns out actually now you can do them, and that's really fun as well. So yeah, I think it's also a good thing to point out that we don't remember everything. Paul says I'm a talking encyclopedia. I mean, there's some stuff that's in there from having worked on it for a long time, but not everything. Oh yes, so there was I was talking about heavy ions, and then I really should wrap up to let people head off. So heavy ions are like if you have a lead atom, which is many protons and neutrons. Don't ask me how many, because again, not a walking encyclopedia, but there's a bunch of them. Somebody in the chat will know. And what we do is we take away the electrons, and then we're just left with the protons and neutrons from the inside, and then we collide these together. And so rather than the protons that we're colliding together to sort of create Higgs bosons and other processes that we want to study, when we collide 82, thank you very much. When we want to collide the heavy ions together, we're creating a very hot, dense plasma of all these quarks and gluons in what we kind of think of as like a soup. And this is very similar to the conditions in the early universe. So if you hear that the LHC is recreating the Big Bang, that's not true. What we're actually doing is recreating the conditions of the early universe, and it's just for a fraction of a second. It's such a very short time, but then we can study how the particles interact with each other, and then how they sort of evaporate off, and how they change as they expand outwards. And so it's a really interesting environment to study. And so ALICE, which is one of the 4 main detectors on the Large Hadron Collider, was specifically built to study this process. But it turns out that ATLAS and CMS that weren't designed to study the quark, gluon plasma also can do a reasonable job at studying it. So it's not possible to. ALICE is like the best for it. It's what they were designed for, but ATLAS and CMS can also do some studies as well. And there are other sites around the world that are also studying heavy ion collisions as well. So there's somebody in the chat who's applying to Birmingham in September to study particle physics and cosmology. Well, good luck. I wish you all the best. Okay, so let's have a quick look. There's a comment here in the chat that I don't understand, but okay. How much coding is involved in your work? You mentioned machine learning. So coding is a really important part of particle physics. So really, if you want to be a particle physicist, I really do recommend working on coding as well. So C++ and Python are the ones that are most commonly used. And then for machine learning, that's a whole other, maybe another video that I can make, because we use many different types of machine learning algorithms to apply to our gigantic data set. But yeah, if you want to be a particle physicist, I really recommend doing some programming. There are fantastic videos on social media that you can watch, and just get started and try something is really my best advice. So you don't have to do anything particularly complicated, but you can write a script to, I don't know, automate something, some numbers. Yeah, I can't think right now because it's a bit late, but there are plenty of things that you can already start trying with. Oh, and actually, what I should say is you can download our open data from CERN, and you can play around with that with programming. So that's also a great way to get some experience of what it's like to be a particle physicist, and try out the data that we have online. Okay, let's have a look. So I really think kind of answered this one. So somebody asked what subatomic particle is my favorite. I didn't say it explicitly, but I'm studying the top quark, so that is my favorite particle right now. It's a really interesting particle because it really allows us to study both precision measurements, as I was talking about, but also search for new to understand dark matter and other potential new physics. So let's see. So the last question I'm going to end with, and then we can continue also in the comments of this video, is what's the most, in my opinion, what's the most exciting thing that has come out of CERN so far? And so there are two things, and CERN is 70, so this year we are celebrating our 70th anniversary, which is yeah, a really huge achievement for the lab. So the two main things that I will say are the biggest, most exciting things that have come out of CERN so far. One is the World Wide Web. Everybody talks about this, but it really is a fantastic product of CERN, in that it's not that it was, so the World Wide Web is different from the internet, before I get those comments, sorry, but I do get them. So the World Wide Web is sort of how the websites talk to each other. So it's like the internet is like, if you have water, the internet is the pipes that the water flows through, and the World Wide Web is the connections and the way to direct the water. And it would have been invented elsewhere, but the reason that it's so fantastic that it came from CERN is that it was created to allow physicists to talk to each other and connect ideas from different websites and host data. And because it was invented at CERN, it is free for everybody on the planet to use. It was released publicly for free. And I know that people have to pay to get onto the internet, but imagine having to pay every single time you wanted to visit a website as well. That would just add a significant amount of costs. And so the World Wide Web was a fantastic thing that came from CERN. And it just kind of shows that, yes, the physics is incredibly important, but also the fact that you bring thousands of people together on really hard problems from all around the world, and just the main motivation is just to increase understanding. You get all of these secondary things that come off too, that are really useful for society. And then the other sort of really exciting thing that came from CERN is the discovery of the Higgs boson. It took over 50 years to discover this particle that had been proposed as a reason why particles have mass. And it took the construction of the Large Hadron Collider, which is the biggest particle accelerator we've ever built, and thousands of people to come together to discover this particle. And we did it because we wanted to know more about how our universe works. And it's just, for me, it's really beautiful that we have this motivation and that we come together to do this work. And we don't yet know what benefits we will get from discovering the Higgs boson, but historically, having understood electrons in incredible amounts of details, and photons and muons and antimatter and other types of particles, we have significant technology that's come from that. We have transistors, we have positron emission tomography, so scanners that allow us to look inside the human body without cutting people up. We have hadron therapy. You know, we've just got so much technology that has come from understanding these particles in tiny details, that I think it's really important that we also know how they get mass, and who knows what kind of technology we're going to get from that in the future. Okay, so I think we should wrap up now. It's been really fun doing this live with everyone. Thank you so much for joining. Thanks again to Bob from Fundamentally Explained for being in the chat. It's really great of you to have moderated and collected all of the questions. I will try really hard to go through and answer the ones that I can see. So if you didn't get your question answered, you can drop it down in the comments for this video, and I will try and go back through those. Otherwise, drop it in a comment from a different video and I'll try and do as many as possible. So thanks so much for joining from TikTok. Thanks for joining from YouTube. And yeah, I will see you around on the internet and talk another time. So yes, thanks for joining. And if you're not subscribed already, please do subscribe, because yeah, it will make me happy to hit a nice round number. It doesn't really mean anything, but it's just, it's nice to have goals. So thanks, and good night. And please do come and join the live on Wednesday with perimeter. So we will see each other again then. Okay, thanks. And then as always, I have to find the off button.